Hello everyone. Let's analyze. Let's begin our analysis today by considering the Texas waffle, ubiquitous at hotels and motels throughout Texas. We could think of it as a contraction of Texas, Texas made small. In fact, if you're eating a waffle in the shape of Texas, in the state of Texas, there's a point on the waffle that is directly on top of the point that you're eating the waffle in Texas. Of course, if you're not in Texas, go to Texas and we'll start this video all over again and hopefully you'll get the point. But the idea is, if I were to shrink Texas into this waffle and then shrink the waffle in the exact same manner, eventually the shape of Texas would shrink to a point directly on top of the point in the waffle that corresponds to the point in Texas that you're eating it. Let's discuss this important Texas-shaped idea. So today's lecture is on the contraction mapping principle. Well, what do we specifically mean by a contraction? I mean, we have a general sense that if we contract, we make things smaller, and that's essentially the idea. Of course, if we make things smaller, we have to have a way of measuring the distance of things to know that things were made smaller. So a contraction requires a metric space to operate. Specifically, a function f is a contraction if it maps one metric space to another metric space, and there exists a non-negative number k strictly less than 1, so that for every x and y in the domain of f, the distance between f of x and f of y is less than or equal to the distance between x and y times k. Where again, k is a non-negative number less than 1. So a way to read that inequality is that the distance between f of x and f of y is strictly less than the distance between x and y. So let's see a fairly simple example. Suppose f maps real numbers to real numbers. F of x is 1/2 x plus 2, and that we're going to imbue the real line with the absolute value metric. Well, then the distance between f of x and f of y is half the distance between x and y. Right? Visually, we can see that the red line is half the length of the magenta line. That magenta line, when mapped by f, got contracted. Right? It got squeezed to half the size. So f would be an example of a contraction. Let's take a look at another example. Suppose f maps n-dimensional vectors to n-dimensional real-valued vectors, where we're imbuing our n-dimensional Euclidean space with the Euclidean metric. And suppose that f is an affine transformation, meaning it's a linear transformation plus a constant. It's a times x plus a. A is a vector in n dimensions. A is a square matrix of real values. And suppose that A has the property that the supremum over all vectors a distance of 1 from the origin gets mapped by A to a distance of sigma or less, where sigma is less than 1. In other words, if I apply A to the unit ball, right, all vectors that satisfy this are vectors on the boundary of the unit ball, or the unit circle. If I apply A to all of these vectors, then the unit ball shrinks. The distance of my mapping AX is less than the distance of x from 0. So a linear algebra note, that supremum property is equivalent to just saying that the 2 norm of A, which is also the largest singular value, is less than 1. F is a contraction because the distance between AX plus A and AY plus A is equal to, well, the norm of A times the difference of X minus Y. Right, here we're using the linearity of matrix vector multiplication. I can multiply that by 1, but with style and purpose, by multiplying by the distance between x and y and dividing by the distance between x and y. Then by using the scaling property of the norm, I can pass in the 1 over the distance between x and y. Using the linearity of matrix vector multiplication, it's equal to A times x minus y scaled by the reciprocal of the norm of the distance between x and y. In other words, this is A times the normalization of x minus y. Right? X minus y divided by the norm of x minus y is a unit vector, so long as x minus y is not 0. Now, since I have A times a unit vector, I know it's bounded by the supremum of A times all unit vectors, which is equal to sigma, which is less than 1. Of course, the distance between x and y is equal to the 2 norm of the difference. So since sigma is less than 1, we have a contraction. In other words, if A shrinks the unit ball, then A is a contraction. And the affine function AX plus A is a contraction. So let's see this played out. Here I have a view of two-dimensional space, and so suppose that I apply to this set of points in 2 dimensions. These set of points happen to trace out the state of Texas. If I apply a contraction, in other words, if I apply to every 2-dimensional coordinate A times the coordinate plus a 2-dimensional vector, where the norm of A, the 2 norm of A, that is the largest singular value, is less than 1, what happens? Does Texas shrink? In fact, it does. It gets smaller and smaller and smaller. Right, so here we see an example of a contraction being played out. Right? If I took any 2 points on that original, those points are made closer together in the orange and even closer in the yellow when I apply the contraction again. I apply the contraction again to get the purple, and the 2 points are made even closer together. Same thing for the green, the blue, etc. If I apply the contraction repeatedly, I keep on shrinking. Now, by the way, suppose I take a point in my space and repeatedly apply my contraction. Well, it looks like it might be getting closer and closer to something. Let's zoom in and see what's happening. Right, there we are on a contracted Texas. We can imagine what keeps happening, right? The same thing happens. It's almost like a fractal when you zoom in and you see the same occurrence happening. Well, what happens to those points if I apply my contraction to those coordinates represented by the red dot over and over? Well, it looks like it converges to a point. Does that always happen when you have a contraction? Do you always get the case that if you apply a contraction to some arbitrary point repeatedly, you converge to some perhaps stationary point? Well, let's investigate that idea. So here we come to the highlight of today's lecture, the contraction mapping principle. And it is essentially the principle we saw played out in the animation just now. Let XD be a complete metric space. So X is the space, the set, and D is the metric. When we say it's complete, we mean that every Cauchy sequence has a limit in the space. And suppose that phi is a contraction, but it's a contraction that maps X to X. Another way of thinking about that is that the range of phi, or the image of phi of X, is contained in X. Then there exists a unique fixed point X star in X. Furthermore, for any starting point in your metric space, the sequence defined by the recursion xn plus 1 equals phi of xn is convergent to that fixed point. So that's exactly what we saw played out in the previous animation. Those red dots were created by a recursion, and those recursions appeared to converge to some fixed point. In fact, the entire boundary of the state of Texas was also converging to that fixed point if I let it recurse, iterate. If I let it iterate forever. So we want to prove the theorem, but what do we know? Right, we know that my metric space is complete, right? Meaning that if a sequence is Cauchy, then its limit exists and is in X. We know that phi is a contraction. In other words, the distance between a mapping of f of x and f of y is strictly less than the distance between x and y. Specifically, it's less than or equal to a number strictly less than 1, greater than or equal to 0, times the distance between x and y. Okay, what are our goals? What do we need to prove to say that this theorem is true? Well, we need to prove the convergence criteria. We need to prove that the sequence generated recursively by applying my contraction converges. Right? What do we mean when it converges? Well, you know what it means. For any epsilon greater than 0, there exists n, yada, yada, yada. Did I just yada, yada, yada convergence? I suppose I did. We also need to prove the fixed point criteria, that if x star is the limit of this recursively generated sequence by applying our contraction recursively, then x star is a fixed point. In other words, phi of x star equals x star. And we need to show uniqueness. That is, if phi of x star equals x star and phi of y star equals y star, in other words, if x star and y star are both fixed points, then they both have to be the same. They have to be equal to each other. You might imagine how that might go. The distance between x star and y star has to be made less by applying phi. But of course, I'll get the same distance. So let's prove our result, and we'll go item by item. So let's prove convergence. Let x naught be some starting point in x, and let's define our recursion. The new x is phi times the previous. Then the distance between the next iterate and the previous, in other words, the distance between xn plus 1 and xn, is equal to the distance of phi of xn and phi of xn minus 1, because that's what xn plus 1 is. It's phi applied to xn. Xn is phi applied to xn minus 1. Because phi is a contraction, we can bound that. It's less than or equal to k times the distance between xn and xn minus 1. Remember, phi shrinks the distance between xn and xn minus 1, so that's why we have that inequality. Now, of course, that distance, by the same reasoning, is less than or equal to k times the distance between xn minus 1 and xn minus 2. And well, I could repeat that until I get to the distance between x1 and x0, and I'll be building k's as I go. So the distance between xn plus 1 and xn is less than or equal to k to the nth power times that original distance, the distance between x1 and x0. And remember that k is strictly less than 1 and non-negative. Now, the distance between xn and xn plus L, so L is later on some point in my recursion, is less than or equal to the distance if I took a detour to xn plus 1. Right, that's just an application of the triangle inequality. Right, if instead of going from xn to xn plus L and computing that distance, I detoured to xn plus 1 and then went to xn plus L, right, then either that trip took me longer or it took me the same amount of time if xn plus 1 was on the way. Well, applying the triangle inequality repeatedly, I could detour to every iterate between xn and xn plus L. And because these distances are between successive iterates, right, we can bound them using this result here. And so that's what we have there. Of course, the distance between x1 and x0 is common in all. I can factor it out. I can also factor out a k to the n. By the way, that's a typo. That should be n plus 1 following the structure of my bound. Let me go ahead and fix that. There we go. It's fixed. So I have k to the n times the distance between the original point and the first iterate times the sum of 1 plus k squared plus all the way up to k to the L minus 1. Well, that's equal to k to the n times 1 minus k to the L over 1 minus k times that original distance. I got this equality by just multiplying this times 1 minus k and then dividing by 1 minus k, and you'll see that it simplifies to this. Now, of course, k to the L, remember that k is between 0 and 1, right? Greater than or equal to 0, strictly less than 1. So 1 minus k to the L is some number also between 0 and 1. So this is less than or equal to if I just got rid of this term. And I want it to be less than epsilon. So this inequality is a hopeful inequality, right? I want it to be less than epsilon because if it is, right, for n large enough, then I have my Cauchy criteria. So what do I need for that to be true? Well, this is true if and only if k to the n is less than epsilon times 1 minus k over that original distance. Remember, I need to make sure that n is large enough, so let me isolate n. Right? N is equal to the log k of k to the n, so I can take the log of both sides. Now, if I take the log of both sides, the inequality flips because the log with a base between 0 and 1 is a decreasing function. Of course, the log of k to the n asks what number do I have to raise k to equal k to the n? Well, k to the n equals k to the n, and that's why I get this. So, if n is any integer greater than some integer big N, which is greater than this for an epsilon, then the distance between xn and xm, right, I'm calling n plus L m, is less than epsilon, which is the Cauchy criteria. So I have that my sequence is Cauchy. Now remember that I'm assuming that my metric space is complete. Therefore, any sequence that is Cauchy is also convergent to a point in X. So I have a limit. we'll call the limit x star. I need to show that x star is a fixed point. Now, note that phi is uniformly continuous. Because if the distance between x and y is less than delta, and I set delta to be epsilon over k, where epsilon is an arbitrary positive number, then the distance between phi of x and phi of y is less than k times the distance between x and y, which is less than k times delta, which is epsilon. Because my choice of delta depends only on epsilon and not on where I'm applying phi, not on x and y, that implies that phi is uniformly continuous. So it's not just continuous, it's uniformly continuous. And because it's uniformly continuous, phi of the limit as n goes to infinity of xn is equal to the limit as n goes to infinity of phi of xn. The limit can pass to the outside because of the continuity of phi. What is phi of xn? Well, that's xn plus 1, right? That's the definition of the recursion. And, well, if xn converges to x star, then so does xn plus 1. Also converges to x star. So I have that phi of x star is x star. So x star is a fixed point. Now, uniqueness. Right, and we discussed that briefly. Suppose phi of x star is x star and phi of y star is y star. In other words, x star and y star are both fixed points. The distance between x star and y star is equal to the distance between phi of x star and phi of y star. But because phi is a contraction, that's less than or equal to k times the distance between x star and y star. Well, if k is strictly less than 1, then this is impossible. So in order for this to be true, we would need k to be 1 or greater, which again contradicts the hypothesis. So the only way that this is true is if the distance between x star and y star is 0. And if the distance between x star and y star is 0, then x star has to equal y star. So we have our uniqueness property. So we've shown each of the 3 items we needed to prove that this theorem is true. So we've completed our proof. So a corollary, suppose xd is a complete metric space and phi maps x to x. If phi to the kth power is a contraction, then phi has a unique fixed point. All right, so notice that we're not assuming here that phi is a contraction, but rather that phi to the kth power for some integer k is a contraction. And the proof is left to the fearless reader, or viewer, as it may be. But let me just note that by phi to the k, what I mean is the composition of phi with itself k times. Or put another way, phi of phi of phi of phi of k times of x. Now, before I leave you with the task of completing this proof on your own, and I know you can, I believe in you, let me just point out that phi k of phi x, that's k plus 1 applications of phi. So I could say that's the same thing as phi of phi to the k of x. In other words, I could apply 1 application and then k applications, or I could apply k applications and 1 application. It's the same thing. And phi k is a contraction. Okay, so now that we have the contraction mapping principle as a true theorem under our belt, let's wield our power. What can we do with it? Well, if you recall back to your ordinary differential equations class, you had a theorem for existence and uniqueness of first order initial value problems. And it was different if f was linear, because you could actually just build the solution and show it has to be unique. But if f was not linear, or if you didn't assume anything about f, your rate function, then there were certain conditions in which you got existence and uniqueness on some open interval that was undefined. So we're going to prove it. We're going to prove that an initial value problem, as described, has a unique solution if f maps, right? F is of course a function of t and x. So f maps some open set in R2, and f is Lipschitz continuous in the second component. That is, there is some Lipschitz constant k greater than 0, for which the absolute value of f evaluated at some point minus f evaluated at another point with respect to the second component, x1, but the first component, t, remains the same, is less than or equal to k times the distance between x1 and x2. If that's true for every pair in U, again, every pair where the first coordinate is the same, then the initial value problem has a unique solution on some interval, t naught minus delta and t naught plus delta, for some number delta greater than 0. So our approach is we're going to define a mapping, phi, from functions to functions. Right? So little phi is a function, and it's going to get mapped by big phi to this function of t. Right? Tau is our integral variable, so after we take a definite integral, we'll get a function of t. Now, if big phi has a fixed point x, in other words, big phi of x equals x, then x solves the initial value problem. Right? If x of t equals big phi of x of t, which equals to x naught plus the integral from t naught to t, f of tau comma x, then, well, x of t naught equals x naught plus the integral from t naught to t naught, which is 0, and x prime equals f of t comma x, thanks to the fundamental theorem of calculus. So that's our goal, is to show that big phi has a fixed point. How do I show it has a fixed point? Well, if I can show that big phi is a contraction, mapping a metric space onto itself, then it must have a fixed point. Of course, this set should contain the solution because the fixed point will be in the set. So, since f maps U to R, where U is a subset of two-dimensional space, is continuous, remember f is continuous, then there's some ball in U centered at t naught comma x naught for which f is bounded. And let's call the bound L. Right? How do we know? Well, if it wasn't bounded inside the ball, then it would have some discontinuity at the boundary of the ball, which is inside of U. Suppose delta is some number less than 1 over k for which the rectangle, illustrated here in blue, is contained in the ball for which f is bounded. So I have some blue rectangle. Right? The width of the rectangle is 2 times delta, and it's centered at t naught. The height of the rectangle is 2 times L delta, centered at x naught. And this rectangle is contained inside my ball for which f is bounded by some given number L. So let x be a set of functions. Specifically, x is going to be the set of all continuous functions that pass through the left side of the rectangle and out the right side of the rectangle and passes through the center of the rectangle, t naught, x naught. So the red curve and the magenta curve are both examples of functions in big X. Right. So this condition here means that my function passes through the center of the rectangle. This condition means that my function passes through the left and right side and not out the top and bottom. And of course, this condition means it's a continuous function. So I claim that phi is a contraction on x using the soup metric, constrained to the domain t naught minus delta, t naught plus delta. Now, if I make that claim, I need to show, 1, that x is complete, and that phi of x is contained in x. And 2, I need to show that the distance between two functions mapped by phi is less than or equal to some non-negative number that's strictly less than 1 times the distance of the original two functions, where again that distance is measured using the supremum metric. So let's show these two things. So for 1, the completeness of x follows from the completeness of continuous functions over closed intervals. Why do I know that continuous functions over closed intervals is a complete set? Well, if a function is Cauchy under the supremum, then it converges uniformly. And if it converges uniformly, it must converge to a continuous function using a result from our second week. So now, of course, x is a subset of this space of continuous functions, but it's a closed subset. So x is complete. Now, phi is Lipschitz continuous. Now, how do I know that it's Lipschitz continuous? Well, remember, the outcome of big phi applied to little phi is a function of t, and that function of t is what I'm saying is Lipschitz continuous. Well, because if I apply it at t minus s, then I just get the integral from s to t times f. But f is bounded by L. So if f is bounded by L, it's less than or equal to the integral from s to t of L, which is that. And so that's the definition of Lipschitz continuous, which is, of course, stronger than continuity. So we get that phi, big phi of little phi of t, that function is continuous. And because it's continuous on a closed interval, it's uniformly continuous. In fact, because it's Lipschitz continuous, it's uniformly continuous. Of course, if I apply my function that's mapped by phi, if I evaluate it at t naught, of course I get x naught, because the integral from t naught to t naught is 0, since my integrand is bounded. Now, let's consider the difference between big phi of little phi of t and x naught. Well, using the same reasoning as before, this is equal to the integral from t naught to t of f. Remember, f is bounded by L, so this is less than or equal to L times t minus t naught. And if you recall the rectangle in our previous picture, t minus t naught is less than delta. So that means that this function passes through the left and right side of that rectangle. In other words, the distance between this and x naught is less than L times delta. So therefore, phi applied to any function in x is contained in x. Now we need to show that that phi is a contraction, right? Result 2. The distance between big phi of little phi 1 and big phi of little phi 2 is equal to, by definition, the supremum over all t in my interval of the difference between big phi of little phi 1 and big phi of little phi 2 evaluated at t. Well, what is that difference? That difference is the integral from t naught to t of f of tau phi 1 of tau minus f of tau phi 2 of tau. I pass the absolute value inside the inequality by using the triangle inequality for integrals. That's why I have a less than or equal to here. But notice that tau is the same here, so I can use the Lipschitz criteria of f. Remember, f is Lipschitz in the second component. So if I use that Lipschitz bound, I get this is less than k times the integral from t naught to t of these two functions. Now remember, these two functions, phi1 and phi2, right, we saw an example in red and magenta in the previous picture, right, are bounded by how far away they can be from each other. Furthermore, the distance between t0 and t is also bounded by delta. So this integral is less than this distance times the largest this integrand could possibly be, the supremum of the integrand function. And of course, we know that the largest this can possibly be is exactly the definition of the distance between phi1 and phi2. Now, by construction of delta, k times delta is strictly less than 1. And since k times delta is strictly less than 1, phi satisfies the condition of a contraction. So it's a contraction operating on a complete metric space that is mapped to itself. So by the contraction mapping principle, big phi has a unique fixed point. And as we pointed out earlier, that unique fixed point must be the unique solution to the initial value problem. So this is a really important theorem in numerical analysis, the Weierstrass approximation theorem. If f is a continuous function on a closed interval, in this case, let's say 0 to 1, then there is a polynomial arbitrarily close to f. In other words, for any epsilon, there exists a polynomial whose distance between f and p is less than epsilon. This is important because a lot of numerical methods basically replace difficult or stubborn functions that are nevertheless continuous with polynomials that are nearby. For example, imagine I want to approximate the integral of a continuous function, but there's no closed form way to do it or straightforward way to do it. Well, this says I can actually find a nearby polynomial, and then I can just integrate the polynomial because polynomials are easy to integrate. Maybe I want to approximate the derivative of a function. Find a nearby polynomial, take the derivative of the polynomial. This theorem tells me that so long as f is continuous, there's always a polynomial nearby. How nearby? As nearby as I want. In fact, the Bernstein polynomial, defined by that expression there, converges to f uniformly. Now, the Bernstein polynomial is quite useful analytically, and it's going to be a useful tool in proving the Weierstrass approximation theorem. But it's not typically the polynomial used when you want to find something nearby a continuous function. Families of polynomials that we typically use would be Legendre polynomials or Chebyshev polynomials. But of course, you'll learn more about that in a numerical methods course. But in this scenario, we're going to use the Bernstein polynomial and show that it gets arbitrarily close. So let's begin with the binomial theorem. It's just a formula for expanding x plus y to the nth power. This is going to be useful, so let's label that 1. If you're taking notes, I would make sure to write that down and label it. Let's differentiate 1 with respect to x and then multiply by x. We would get that expression there labeled 2. And again, I would pause here and write that down. And if I differentiate 1 twice with respect to x and then multiply by x squared, I get the expression there labeled 3. So again, I would write down that expression and mark it. Now we're going to define this RK polynomial to be equal to this. And what does this have to do with anything? Well, it'll come up. Let's insert y is equal to 1 minus x into expression 1. If we insert it into expression 1, right, replace y with 1 minus x and y with 1 minus x, we get this. And of course, notice that this expression is precisely RK. Right, so we're essentially going to just be simplifying this. Now x plus 1 minus x is 1, and 1 to the nth power is 1. So we see from this expression here that 1 is equal to the sum from k equals 0 to n of rk of x. Well, that's pretty useful. If I also insert y equals 1 minus x into expression 2, I get that x times n is the sum from k equals 0 to n of k times rk of x. And if I insert y equals 1 minus x into expression 3, I get x squared times n minus 1 equals the sum of k times k minus 1 times rk. Of course, if I take this and expand it out, I get the sum of k squared rk minus k times rk. We know what k times rk is. It's x times n. So in fact, I could use those results of inserting y equals 1 minus x into the expressions 1, 2, and 3, and note that this expression is true. So for now, you can take my word for it and just follow along with the idea of the proof, but if you want to stop here and make sure that you understand why that equality is true, it's just a little bit of arithmetic of the expressions above. Now, since f is continuous on a closed interval, it's uniformly continuous, right? So we all know what that means by now. We have it recited by heart. For any epsilon greater than 0, there exists delta greater than 0, such that x minus y is less than delta implies f of x minus f of y is less than epsilon. Definition of uniform continuity. Because f is uniformly continuous on a compact set, it has a maximum. Let's call the max value m. So the difference between f and Pn, where Pn is that Berenstein polynomial that we defined, is equal to f of x minus f of k over n. Now, what is k over n from k equals 0 to n? Right, those are just n plus 1 evenly spaced points from 0 to 1. That's all that is, times these rk polynomials. Now remember, if I sum up all the rk polynomials, I get 1. So if I put f inside my summation, I get equality, because if I were to distribute, I get f times rk. This is not indexed by k, so I can take it out and have the sum of rk, which is 1. Now, notice this term here is f of x, and this is f evaluated at evenly spaced points. And I'm considering a particular x here, right? A particular x. So x is either close to one of these discretized points or it's not. Now when I say close, how close? Delta close. So we're going to split this sum into indices for which x and k over n is within delta and all the others. So when I say k delta, I mean all indices k for which k over n minus x is less than delta. Because for those indices, this is less than epsilon, right? According to this criteria here. So in other words, if these evenly spaced points are sufficiently close to x, we can bound this by epsilon. These we cannot. These are all the other indices for which this is not true. So this is not necessarily less than epsilon. Well, if this is not necessarily less than epsilon, this had better be small enough, because we want the whole thing to be small. So let's distribute that absolute value, right, using the triangle inequality. So now we have an inequality, the absolute value of this difference, the absolute value of this plus the absolute value of this. Of course, we know that that's less than epsilon. We know that this is less than or equal to 1, because if I sum up all of them, I get 1, and they're non-negative. This is less than m, and this is less than m. Remember, f is bounded. So plus 2m times this. Now, of course, 2m is not small. So I need this to be small. I mean, it's not necessarily small. I need that to be small. This is 1 times epsilon. It's as small as I want. Epsilon's arbitrary. I need to show that this is small if I'm going to get my result. Now, notice if k is one of the indices in k not delta, in other words, x minus k over n is not less than delta, specifically it's greater than or equal to delta, then I can scale both sides by the reciprocal of delta. I would get this inequality. I can square both sides because squaring is a increasing function. So I get this squared is greater than or equal to 1. Or 1 is less than or equal to this. Right? Two different perspectives of the same thing. So if I take that expression, 2m times the sum of rk, for all k not within delta of x, it's less than or equal to if I were to scale by this number that's greater than or equal to 1, which is what I have here. If you remember, when we plugged y equals 1 minus x into our three terms, and I said you could combine them to get that expression, well, now we're using it. That gives us this inequality here. And that's less than m over 2n delta. Well, how did I get rid of this? Well, x, right, notice this n and this n squared, right? The square cancels and this n cancels. So x times 1 minus x over the interval 0 to 1 is less than or equal to 1/4, right? We could plot that and see it's less than 1/4. And well, this goes to 0 as n goes to infinity. So all I have to do here is just choose n to be large enough. If I choose n to be large enough, then this term is small enough. And we have our result. So long as n is any integer greater than or equal to some big N, which is some integer greater than m, right, the bound of f, divided by 2 times delta squared times epsilon. Right, and for any epsilon, I can find such a big N. If that's true, the difference between f minus Pn is less than 2 epsilon. And that's true for every single x in 0 and 1. Right, notice that my bound is no longer dependent on x. It's independent of x. Right? So this is true for all x, right? Which is why we can say we get this uniform convergence. Stone-Weierstrass is essentially a generalization of the result we just saw, the Weierstrass approximation theorem. If you have a metric space and a subset of the metric space is compact, and if B is a set of continuous functions mapping that compact subset A to R, and B satisfies the following conditions, B is an algebra. In other words, B is closed under addition, multiplication, and scaling. F of x equals 1, right? 1 is an element of B. Then for every unequal pair x and y, there is a function in B for which f of x and f of y are not the same. Then we say that B is dense in the set of continuous functions. What do we mean when we say that B is dense? It means that there's an element of B arbitrarily close to every element in C, A, R. In other words, the set of all continuous functions. Another way of expressing that is that the closure of B, in other words, if I take B and add to the set all of its accumulation points, then I get exactly the set of all continuous functions on A. So that's perhaps a bit more abstract than we're going to use in this semester, but it's good to know, and we should just observe that the conditions of B is satisfied by the set of all polynomials. In that case, we get the previous condition, the Weierstrass approximation theorem. That's it for today.